Hello, I hope you're doing well and welcome to Algorithm. If you ask a mathematician, physicist, or even ChatGPT about the most beautiful number sequence, the answer is probably Fibonacci. Let's consider this sequence of numbers that starts with 1, 1, you add them together to get 2, and then you add the last two elements that are 1 and 2 to get 3, etc. till infinity. This elegant sequence, often illustrated with these colorful rectangles where each new rectangle is the sum of the last two, can be defined mathematically by these equations. You start with 1 for the first two elements, then you simply add the last two values, like this. F of n is f of n minus 1 plus f of n minus 2. Beyond its beauty and appearance in nature and art, today we're talking about something equally important. That's how to compute f of n. So let's say we have a number n and we want to write a program to make the computer calculate the nth Fibonacci number effectively. First, the classic and extremely slow recursive approach that nobody likes. The simplest way to compute f of n is by literally following the definition. We could write a short Python program with function that returns 1 for the first two numbers and then calls itself recursively to find the values for the last two numbers. This approach is straightforward and correct, but there is one small problem. Actually, it's a huge problem. It's slow, like painfully slow. I mean, if you try this method on larger Fibonacci number like 50 or 60, your computer might need years to finish it. Let's see why. To compute f of n, the computer needs to know f of n minus 1 and f of n minus 2. And for f of n minus 1, it also needs f of n minus 2 again and f of n minus 3. So the problem quickly gets bigger, and we can mathematically prove that the complexity of this algorithm is 2 to the power n. I mean, it explodes when the n increases. Dynamic programming, aka memoization. In dynamic programming or memoization, you can think of it as using memory to help us by storing computed values so we don't have to recompute them again. We can apply this technique to our Fibonacci problem as follows. Each time we compute a new Fibonacci number, we save it in a table or a cache. This way, to compute the next Fibonacci number, we just need to check out the last two numbers in the cache. With this new approach, our time complexity is big O of n, since we're only filling table with n elements. And our memory complexity is also big O of n, because we're storing n values in the memory. This is already a massive improvement, but there is a catch. We need a lot of memory for large numbers, which can be hard for bigger values of n. Well, actually, there is a tiny improvement. We don't actually need to store every single value, as we're not looking at all of them at the same time, but we're actually looking only at the last two values. So the key improvement is that instead of storing the whole table, we may only store the last two elements. Let's call them A and B, and let's design this new algorithm that works perfectly with only constant space. But can we go faster? Faster, faster, Hamuda. Yes, we can go faster by this fast matrix multiplication. Alright, here's the trick. Consider f of n and f of n minus 1 as a vector. This can be expressed by the product of the matrix 1, 1, 1, 0 and the vector f of n minus 1, f of n minus 2. If you forget how to multiply two matrices, that's fine. It's only line by column, so you can see the formula right here. And now repeating the multiplication operation on the resulting matrix, show that we can keep simplifying using the associativity property of matrices. I mean, we can gather the first two matrices to get 1, 1, 1, 0 to the power 2, and then multiply it by the remaining vector. And we can repeat this process again n times until achieving this form. And now, by using the fast exponentiation as covered in the last video, you see I made video that will be useful in the future. We can compute the matrix exponentiation in log of n time complexity only, Binet's formula. So there is one more thing that's even faster, but it's not correct. Let's see. Actually, it's Binet's formula. This formula can compute f of n, as you can see here, using a single step with this golden ratio. That's phi. That's 1.1618, etc. The problem with this formula is we cannot use the computer to accurately store phi because there is infinity of the values after the point. So this method can be seen as an approximate method, but we cannot prove mathematically that it gives the exact number using the computer. So to show the efficiency of this method, I coded each of them and plotted the result. For small values of n, they all work fine, but as n grows, the difference became apparent. First, we can see that the classic recursive method become inefficient past values like 30 or 40, while the dynamic programming stays fast until the fast exponentiation method finally pulls ahead for very large numbers of n. I'll drop a GitHub link below if you want to try it yourself. So here's the summary. Finally, there's various methods to compute f of n, where the complexity varies from 2 to the power n till log of n for the exact method and constant time for an approximation. Each of these methods has its corresponding space complexity too. So here's my final thought. Algorithmic study does not only mean finding a solution to the problem, but it means finding a solution that works, a solution that can scale when instances became harder, bigger, and more complex. This is why the study of algorithm is always related with a related field that's the study of complexity of the algorithm. The complexity analysis of this algorithm indicate whether this algorithm works fine or not. And the improvement of such a complexity, this was leads the researchers and some engineers in labs and companies to improve upon their product in terms of efficiency and scalability. This was all for today. I hope you guys liked this video. If you did, please subscribe to my channel.